Every single day, millions of gallons of perfectly treated, highly pressurized drinking water leaks directly into the soil. It never reaches a faucet. It escapes pressurized distribution grids through thousands of microscopic fractures and catastrophic ruptures alike. Utility engineers divide this infrastructure failure into two distinct categories. Apparent losses represent water that is consumed but not paid for, due to metering inaccuracies or unauthorized connections. Real losses, however, are the actual physical leakage from deteriorating pipes, valves, and underground service connections. To quantify this hemorrhage, utilities rely on a strict auditing framework called the Water Balance Matrix. It maps the total volume of water pumped into the system and tracks exactly where it ends up. The matrix reveals a precise mathematical gap. By taking the system input volume, the total amount of water produced, and subtracting the billed authorized consumption, engineers define the remaining volume as non-revenue water. It represents the exact volume of water a utility spends money to treat and pump, only to lose entirely. Finding the source of this lost volume is a massive logistical challenge. You cannot solve it by sending crews to blindly search for wet pavement. Eliminating physical leaks across an entire city requires a top-down spatial isolation strategy to systematically shrink the search grid. When the public thinks of water loss, they picture a geyser erupting through an intersection, but the true threat to a utility's capacity is entirely silent. It is the slow, invisible pipe leak, running continuously underground for months. This chart illustrates loss volumes. A sudden main break loses 153 gallons a minute, but is repaired in 3 hours, capping loss at 27,000 gallons. A small service leak loses only 4.5 gallons a minute, but over 46 undetected days, total loss approaches 300,000 gallons. These hidden, long-duration leaks are constantly aggravated by cyclical transient pressures, often referred to as water hammer. Every time heavy pumps cycle on or industrial valves shut rapidly, hydraulic shock waves travel through the grid, expanding existing microfractures in aging metal and PVC. Finding one of these small service leaks across thousands of miles of buried pipe is impossible through surface observation alone. The search area has to be drastically narrowed. Utilities must move beyond reactive, visual inspections. The only viable method to locate long-duration leakage is to physically partition the network and use precise volumetric math to prove exactly which neighborhoods are bleeding pressure. The foundational step in this process is establishing a district metered area, or DMA. It breaks a massive, unmanageable municipal water grid into small, tightly controlled sectors. Engineers create a DMA by permanently closing specific boundary valves along the perimeter of a neighborhood. They leave only 1 or 2 inlet pipes open, outfitting them with dedicated bulk flow meters. Before any data is recorded, the sector must pass a zero-pressure test. Crews shut off the inlet valves and verify that the water pressure inside the sector drops to 0. This mathematically proves the zone is hydraulically isolated, with no unknown pipes feeding water from the surrounding grid. With the boundaries sealed, the bulk leaders begin tracking every drop of water entering the DMA. The critical metric engineers monitor here is the minimum night flow. Between 2 and 4 in the morning, baseline consumer demand drops to near 0. If the bulk meter registers a high continuous flow rate entering the DMA during this deep night period, that water is draining straight into the soil. The minimum night flow isolates the exact volume of physical leakage for that specific sector. This volumetric data confirms that a specific neighborhood has a severe leak, but it provides zero spatial data. The meter cannot tell you where along the 5 miles of isolated pipe the failure actually sits. Once a DMA is flagged as non-compliant, the macro-level audit is complete. Field crews must deploy into the flagged sector, relying on micro-level acoustics and physics to pinpoint the exact failure. For decades, crews searched for leaks qualitatively. A technician would walk the pavement, listening through ground microphones for the distinct hiss of escaping water. But for deep pipelines or tiny fractures, human hearing is entirely insufficient. This diagram illustrates a leak noise correlator setup, shifting detection to automated calculation. 2 sensitive acoustic transmitters are attached to the pipeline, bracketing the failure. Escaping water under pressure creates acoustic waves radiating outward in both directions along the pipe wall. Unless the leak is dead center between the two sensors, the noise will hit one transmitter before the other. This creates the first critical variable, the signal time delay. To calculate the exact leak position, represented by the variables at the bottom, the central receiver requires two inputs: the total distance between the two sensors and the exact velocity of sound traveling through that specific pipe material. Sound travels at a very different speed through iron than it does through PVC. This schematic shows how the unit analyzes acoustic data. The receiver runs a mathematical cross-correlation, sliding the noise signature from the first sensor against the second until the wave patterns align. In the bottom graph, this alignment is marked by the maximum vertical spike. That peak vertical spike gives the processor the exact signal time delay down to the millisecond. Plugging that delay into the algorithm yields the precise physical distance to the leak. The technician now has an exact measurement down the pipe to mark for excavation. Acoustic successfully mapped distance linearly along a pipe. But if the utility's records are outdated and the pipeline's exact physical routing through the soil is undocumented, knowing the distance along a winding, untracked pipe is useless. When dealing with legacy underground networks, utility crews frequently encounter sections of undocumented pipe. If you do not know the pipe's physical vector beneath the pavement, acoustic correlation cannot guide an excavator. This diagram demonstrates pipe locating equipment utilizing electromagnetic induction. A surface transmitter connects to the pipe or a tracer wire, injecting an alternating current. This forces an electromagnetic field, shown by the dashed circles, to propagate upward through the soil. The pipe acts as an antenna. A technician on the surface carries a specialized handheld receiver. This unit is calibrated to isolate and track the specific frequency and field strength radiating from the pipe below, filtering out interference from adjacent power lines. This diagram shows the process in action. Technicians sweep the surface, watching their displays for the strongest signal peak. By following that peak, they map the exact directional vector and burial depth of the buried pipe. A safe excavation requires layering all of these verifications. A utility uses volumetric isolation to flag the zone, acoustic calculation to determine the distance to the leak, and electromagnetic tracing to map the pipe's exact location in the earth. Only then do they break ground. The operation concludes in the trench. Crews expose the pipe, clean it, and install a heavy repair clamp, sealing the fracture and restoring structural integrity. But many utilities make a critical operational error right at this step. They treat the physical clamping as the end of the job, bury the asset, and move on. While a physical repair stops the leak, its value is temporary if the data remains disconnected. A Geographic Information System, or GIS, provides the digital feedback loop needed to integrate this fieldwork into the utility's long-term maintenance strategy. Before leaving the site, field technicians must execute a strict data logging protocol. They record the exact spatial coordinates, the pipe material, its diameter, and the specific mechanism of the fracture. This raw field data is immediately pushed to the central database, registered against the customer's geographic address code, and synchronized with the utility's billing systems. This data upload ensures the operation does not remain a forgotten patch in a dark trench. It transforms the intervention into a permanent, highly searchable historical data point within the digital grid. As crews perform hundreds of documented repairs over several years, the steady accumulation of localized data reveals specific failure patterns across the entire infrastructure grid. This GIS map categorizes pipe materials across the network. Using aggregated data, predicted spatial heat maps overlay the base map. Notice the dense cluster of red lines here. It clearly isolates that legacy amiant pipes fail at a substantially higher rate than surrounding PVC. This multicolored network map displays a heavily interconnected system. By continuously running algorithms against the compiled historical data, GIS modeling visualizes exactly which of these zones are mathematically most vulnerable to future transient pressures. This data transitions the utility from a reactive posture to a predictive one. Instead of waiting for surface ruptures to authorize a project, managers can now prioritize pipeline replacement based on the mathematical probability of the next failure. Reducing non-revenue water is an ongoing engineering challenge. It requires mastering the physics of acoustic correlation and electromagnetic induction in the trench. The true infrastructure resilience comes from digitizing those physical interventions, turning a sprawling, deteriorating pipe network into an actively self-diagnosing digital model.